Okay, hello everybody. In this video we're going to be looking at differentiating e to the f of x. So you may remember my last video that I did, which looked at differentiating e to the x. We're going to build up on those principles that we learnt in that video and do something slightly more complex. So here's a rule I want to introduce in this video, and that is that e raised to the power of f of x, when we differentiate something that's in that form, we're going to get e to the f of x, just as it is, multiplied by the derivative of the exponent that e was raised to, or the f prime of x. So we've got a product between those two terms. Okay, so I've sort of explained the rule that we're introducing in this video, and from that I'm just going to go ahead and show a few examples, walk through it, and hopefully you'll be able to understand and apply this rule by the time that the video's over in about 12 minutes or so. So first off, we're going to look at the very first one, and that is differentiating 4e to the 2x. So to get the dy over dx, we need to think, what rules of differentiation are we going to use? Is it a quotient rule? Is it a product rule? And by looking at it, we can see, no, there's no evident division there, so it's not a quotient rule. There's no evident addition there, so it's not a sum rule. So it looks like it's going to be a product rule. And we can identify that there are two distinct terms there. And the two distinct terms show that there is a first term of 4 and a second term of e raised to the power of 2x. Okay, so now we just go ahead and we use the product rule. And in case you haven't heard the product rule before, I've used it in some of my previous videos, but again it's just taking the derivative of the first term, multiplying it by the second term as is, and then adding the derivative of the second term to the first term as is. So you see we go differentiate, non-differentiate, plus. Then we go differentiate, non-differentiate. So think of it as going differentiate first up, then we don't differentiate, and then we hit a wall and we bounce back, and then we differentiate, and then we don't differentiate. Simple way of sort of thinking about it. Remember that you should end up with 4 sort of distinct terms within the product rule when you finish differentiating it. So again, the dy over dx, and I've said this a few times, but the derivative of a constant, so derivative of our first term, is always going to be 0, because of course it's just going to be a flat line if we were to graph, say y equals 4 for example. Then what we do is we have the second term as is, and that's e to the 2x, but remember, because that's 0 times e to the 2x, anything multiplied by 0 is going to be 0, so really we can actually wipe them away because they're not needed and they're not going to change the equation. So we're halfway through, and what we do now is we take the derivative of the second term. And the derivative of the second term, this is again where we apply e to the f of x, is going to be e to the 2x, because that's e to the f of x, just as it is. And then we take the derivative of the exponent, and the derivative of 2x is just going to be 2, of course. And that's because essentially that's x to the 1. So we bring the exponent down on a holiday to visit its friend number 2. And 2 times 1 is 2, so it doesn't change it there. And that's x to 0, and anything raised to the power of 0, with the exception of 0, is of course going to be 1. And then we multiply it by the first term, as is. And now what we do is we simplify. 2 times 4 makes 8. And then we have 8e to the power of 2x. And we've done that first one, so that's really good. Now we can move on to the next one, and I'll probably go to the one underneath it because that's nice and simple and reasonably straightforward. For this we have 45t e to the power of negative 0.4t. And again, we think about, okay, what rules of differentiation do I need to apply? Oh, I've sort of gone across. In fact, yeah, we'll go across. This one's a reasonably challenging one because you have to think about the negative exponent and you have to think about all the t's and e's there, but it should be fine. So we have 45t and e to the power of negative 0.4t. That's a product rule there. Sorry that I went across instead of down, but that's fine. I know you'll forgive me. So now what we do is we have our two terms, our first term and second term, and we apply the product rule again. So the derivative of the first term, if we have a constant and then we just have a pronumeral that's raised to the power of 1, we know that the derivative is going to, of course, just be 45 there. So we have 45, and then we write the second term as is, to the power e to the power of negative 0.4t. And then what we do is we add on, and I'll put brackets around this to make sure we don't get confused with the negative signs. And from that, what we do is we take the derivative of the second term. And again, this is e to the f of x, so we just follow that format. Again, once you've learnt the rules, you'll see where to apply them, and it will make differentiation easy. So we have e to the power of negative 0.4t, because that's our e to the f of x, and then that's multiplied by the f prime of x. And the f prime of x is, of course, going to be negative 0.4, because again, that's the coefficient of a pronumeral that's raised to power 1. So it's just going to be that coefficient there. And then what we do is we multiply that by the first term as is, which is 45t. And now we could leave it in that format, but we could simplify it, and simplifying it makes it nice and it gives us a more elegant solution. So in order to do that, we just group a few terms together. On the left-hand side of the equation, there's not a lot to simplify, so it's just 45e to the power of negative 0.4t. But here we can see that there's 0.4 and 45, and we can multiply them together because they're multiplied together in the equation. And if we do that, we can get out a graphics calculator. 45 times by 0.4, and that's going to come up to 18. And it's going to be negative 18 t, because that's 45t there. And then that's just e to the power of negative 0.4t on the end there as well, because that's what's left over on the right-hand side. And there we go, we have differentiated these two equations so far, again, using the product rule. But now, let's go to just a simple e to the f of x term and work out how we're able to do this. So this one is one that I probably should have done before because it's slightly simpler, but I'll do it now anyway. So e to the power of 3t squared. And e to the power of 3t squared, again, we have our e term and we have our f of x term. So to work out the derivative, we just need to apply our e to the f of x rule. So we have e to the power of 3t squared, because that's our f of x, and then e to the f of x, and then we find the f prime of x. So what's the derivative of this exponent? Now we bring the 2 down to meet its friend, number 3, and because of that we have a product there of 6, and it becomes t to the power of 1, so it's just going to be 6t is our derivative that we multiply it by. And then again, we can simplify. We can bring the 6t to the front, for example, so we get 6te to the power of 3t squared. And that gives us the derivative, the f prime of x as such, if this were to be a function. Okay, so now we've done those 3 there. Let's go on to a quotient rule, getting slightly more difficult and slightly more interesting as well. So I'll just get rid of these. And what we can do for the quotient rule is we have e to the power of, and I believe that's meant to say e to the power of x there, for example. Can't actually quite read it. In fact, I'll make that e to the power of 3x just to make things interesting. And all over 4e to the power of 5x. So we can see here it's a quotient rule overall, and we can see that down here we have a product rule that needs to be done as well. So, the dy over dx equals, and in quotient rule, we take the derivative of the first term first. So we have e to the power of 3x, and then we multiply that by, oops, probably don't need a bracket that big, but we multiply that by the derivative of our f of x term, again, because of the rule we have up there. So it becomes 3 there. And we could even realistically rewrite this as being 3 e to the 3x like that, just to keep it reasonably neat. Then we rewrite the second term as is, based on the quotient rule. Then what we do is we take the derivative of the second term, and the derivative here, again, we're going to have 0 to the power of e 5x when we use the first term's derivative multiplied by a second term as is, so we're going to go ahead and differentiate the second term and then multiply it by the first term. Now, e to the power of 5x, again that's e to the f of x, so we're going to have e to the power of 5x multiplied by 5. 5e to the power of 5x from that, using that rule there. But then we can group some terms and be clever because we know that the second term's derivative is going to be multiplied by the first term as is. So that's going to be 4 times by 5e 5x. So in that case, it's going to be 20e to the 5x. And then, of course, we multiply that by the top term as is. And then that's all over our denominator squared. So our denominator in this case is 4e 5x. I probably don't need a bracket that big, that's squared. And there we go. We've used quotient rule to be able to differentiate terms that have e to the f of x in it. Hopefully you're able to follow that. That's a reasonably complex example, but again, it'll give you a good understanding of some of the concepts that we have in here. And now lastly, what we'll look at, in fact, second to lastly, we have e to the ln x, and in this case, we can look at this slightly differently because e and ln are going to cancel each other out. So we're going to have just x, which will be any given x coordinate, and from this we actually get a derivative of 0, which is quite an interesting concept. I won't go too much into depth behind that, but you get a derivative of 0 when you have e raised to the power of ln x. And that sort of combines a few ideas together on this, but again I'm sort of running out of time, so I'll just jump straight to the last one, and I'll probably clear off a little bit of board space to be able to do this. But we have e to the power of 3x take 6 all over ln 2x, so it combines that, and those are modulus symbols in case you're wondering, because we have a positive value there. And from that we take the derivative, so we get the dy over dx, and it's a quotient rule, so we have e to the f of x, so we differentiate that, so it's e to the 3x take 6, and we multiply it by the derivative of the exponent is raised to, so in this case it's just 3, because the derivative of a constant is 0, and that'll be x to the power of 0 when we subtract 1 from the exponent, which we do in differentiation. And in fact we could even write the 3 out the front here to make things nice and simple. And then we multiply that by the denominator as is, and then we subtract the derivative of the denominator, and remember in my video I said that ln f of x, ln f of x, the answer would be the f prime of x over the f of x. So we get 2 over 2x, which is going to make 1 over x, because 2 and 2 will cancel each other out there in the numerator and denominator. Remember, see my ln x video if you're confused. And then what we do is we multiply it by the first term as is. And that's all over the denominator from here, so ln 2x and all of that squared. And that's just a little look at how we can use ln and e and differentiating e to the f of x. Quite a few complex ideas here. I did get slightly faster at the end, sorry for that, but I don't want to make this too long, and hopefully get the hang of being able to use product and quotient rule reasonably effectively now, so you could follow along quite nicely. Have any comments, please leave them in the comments box below, and thank you very much for watching, and I hope you enjoyed it.